catastrophic damage and consequences. So this is really one of the more dramatic instances of it. This is that large flow slide that occurred after the Palu, Indonesia earthquake in 2018. This is about 1.5 kilometers scale, 1.5 miles square kilometer flow slide, displacements of up to about 1 kilometer in many areas, just completely wiping out large agricultural lands, residential areas. We see a lot of other types of manifestations of liquefaction. Kind of the telltale sign are sand boils. So this is a part of Christchurch, New Zealand, that famously is still, written off, uninhabited. They have not redeveloped. This is sort of, surface boils, surface manifestation at really large scales, and kind of showing how destructive it can be. When it occurs under shallow foundations, the kind of, as much as you could joke about earthquakes that cause this much damage, the running joke is oftentimes that these buildings actually did pretty well. Their structural systems performed pretty well under the seismic loading, but there was substantial liquefaction under the foundations, causing pretty classic bearing failure, and again, rendering these structures unusable. We also see damage to critical infrastructures, oftentimes due to vertical or lateral deformations, damage to roadways, bridges, potentially embankment dams, San Fernando being a very classic case of really just a mini landslide due to liquefaction in the upstream shell, resulting in, a few meters of freeboard. They got lucky in San Fernando. They could have had much larger collapse. This required, I think, 80,000 residents downstream to be evacuated. But yeah, it's pretty clear pretty easy to imagine what could have happened if there was overtopping. Loma Prieta, this is the Marina District, another very classic example where we have, a gas main rupturing, a fire breaking out. This fire was put out, I think, due to nearly decommissioned fire boats because they couldn't tap into the hydrants because gas mains ruptured, water mains ruptured. And this is, again, due to liquefaction in a lot of the fill that underlies the Marina District in San Francisco. So just this giving you a little picture, and something you guys may already be very familiar with, the types of cascading hazards and risks that come from something like liquefaction. Within the context of risk, we've seen liquefaction can cause pretty substantial direct impacts. These are just direct costs, nothing to do with downtime, economic losses due to downtime, or things being unusable for a while. So we can see that really, at least in the United States, costs can get up into the hundreds of millions of just direct damage. Loma Prieta, Northridge and again, these are kind of distributed across different sectors. Every earthquake is different. The Baja earthquake in 2010 was primarily an agricultural destroyer. You have buildings, residential, transportation, utilities. All these are tied together in a lot of different ways when we talk about the built environment and infrastructure. But we're coming up on 30 years since Northridge really being the most recent high-profile earthquake to cause a ton of damage. And I think in a way, we've gotten a bit complacent at the policymaking level. There's really no reason another one of these couldn't happen tomorrow in any of these high-hazard places. And we've made a lot of improvements in how we handle liquefaction hazards since 1994, but there's probably not enough to avoid hundreds of millions or even billions of dollars in direct and indirect losses. Okay, so let's talk a little bit about liquefaction hazard assessments, and really just some questions we'd like to answer today, some motivating the rest of the talk, which is, like I said before, how do engineers typically handle liquefaction hazards in practice? And then how does this approach fit or not fit is what I'm going to try to argue within the broader context of seismic performance. And then again, like I said in my overview, can we potentially bring the two closer together? Hopefully getting you guys to think a little bit about downstream risks, demands, damages, costs. Okay, so again, this might be very, very familiar to a lot of you, or pretty basic. How many of you have been in consulting or in the private sector in the past and done like a simplified liquefaction analysis? Okay, cool. So this might be more new than hopefully, but surely you've seen this in your classes, hopefully. But typically we start with a very first order susceptibility calculation or susceptibility assessment. It's not really a calculation. This has a number of different approaches where we'll take some samples, or do some field classifications to try to assess the degree of sand-like behavior. Obviously, an assessment of groundwater conditions, going beyond soil composition. This paper, Greenfield and Grant 2020, actually did a lot of probabilistic sensitivity analyses and showed groundwater is maybe the biggest driver of uncertainty when it comes to liquefaction. So using site-specific measurements, regional scale modeling of groundwater can be supplemented. And then obviously looking at previous liquefaction history, looking at geologic maps where they're available, identifying surface units like fill, alluvial deposit, stuff that it's going to be granular, low energy deposition that might require us to start thinking about liquefaction triggering. And this is where we start to bring in earthquake loading for the first time. Typically the results of a seismic hazard analysis. I'm at the USGS, so I don't have to, but I'm compelled, intrinsically compelled to bring up the National Seismic Hazard Model. We also need to be able to more rigorously characterize our soil's resistance to the cyclic loading. Usually the results when we talk simplified procedures are in the form of a factor of safety or probability of liquefaction. These are using simplified procedures that have been kind of calibrated to both lab data, field observations, typically looking at liquefaction, no liquefaction field case histories. If we think that the liquefaction triggering potential is significant, and I'm being intentionally vague here, because if you look at the codes, ASCE 7, then you hear provisions hashed out, any building code or any other seismic provision, liquefaction is really, really vague. So if liquefaction potential is significant, then we have to start thinking about consequences. This might look at alternative characterization of earthquake loading. I'm going to try to move this a little bit higher up. Maybe this guy too.
You get the green arrow underneath, right by your screen sharing.
Okay. Dock the bottom. Amazing. Okay. With the disclaimer in the bottom, still remember that preliminary, don't disseminate. Again, federal government stuff. Okay, so consequences. This is where we might start to look a little bit more at our earthquake loading, try to refine our characterization of earthquake loading. We start to look at system level characteristics. How extensive is our liquefaction? Potential liquefaction, how connected are the soil layers? How not connected are they, both lateral and vertical directions? Surface topography. Importantly, ideally, the characteristics of our structure, but not always in practice. Is the structure actually, characterized? So this is sort of the broad view of how we tend to approach liquefaction. I'm going to spend most of my time today, like I said, not the most compelling part of it, but we're going to focus on triggering today, particularly the factor of safety. And the reason for that is because that's typically where seismic provisions live. When you are getting out there and having to do a minimum design requirements, a lot of this is centered around assessment of triggering, particularly using the factor of safety. So I will start by saying I don't like the factor of safety. It is a legacy parameter that we use to assess liquefaction potential and consequences. And so that's generally where our guidelines have taken us over the years. And so that's where we're going to operate out of today. Okay, so you guys might be familiar with the factor of safety and the simplified cyclic stress-based procedure. This is basically a demand capacity problem, but for soils, our demand is represented via, through most conventional methods, a cyclic stress-based procedure. This requires us to specify the peak ground acceleration as well as the earthquake magnitude, and then compare that to our soil's capacity or cyclic resistance ratio. That's typically a function of relative density, fines content, stress conditions. And then we can look at a lot of these published correlations that give us this limit state between liquefaction and non-liquefaction. And our factor of safety less than 1, we expect that our demands far exceed our capacity. Less than 1, obviously, we would expect unlikely or little soil liquefaction. Again, all very vague, all very kind of qualitative. Sometimes we can think of, if our factor of safety is very low, that means our seismic demand far exceeds our capacity. We might expect liquefaction to occur much earlier in ground shaking. We might expect consequences to be more significant. Okay, what do we use liquefaction factor of safety for? This is based on my conversations with a lot of practicing engineers, my personal experiences as a practicing engineer, liquefaction factor of safety most often is kind of a screening tool. Is liquefaction going to be a problem at our site? If our factor of safety is greater than 1 in most of the critical layers, we're good. We can kind of proceed without having to delve into some special circumstances. And so in many cases, people, if it's less than 1, then we kind of have to start looking at consequences, sharpen our pencils. This is where projects tend to change drastically. More money is invested in refining our analysis. Potentially we pursue nonlinear modeling or some kind of estimate of settlements, damage to foundations. This is where we start to pursue mitigation strategies, alternative designs. It's actually it's a gateway to a lot of headache for stakeholders, which is fine. A lot of times factor of safety is used as an intermediate parameter. Sometimes we use it to estimate surface manifestations. This is using the fragility functions of Guillen and Maurer. Oftentimes to estimate free fields settlements or lateral spreading. Whether or not that's the right approach, I think is something that's being revisited by a lot of really smart engineers in this department, as well as kind of around the country and around the world. Ideally, we tend to take our factor of safety results and use them to inform whether we need to use nonlinear, numerical methods to really start getting more sophisticated analyses of consequences. In either case, though, I've highlighted the word and italicized the word consequences. That's ultimately what we care about. We don't really, it's not enough to just say liquefaction triggering is going to happen at the site. Consequences are what we care about. And so this sort of gets us into the concept of consequences are what we care about. How is our structure going to handle liquefaction? We can start talking about things more generally in terms of a performance objective. And because I'm going to use the word performance objective a lot in the rest of this presentation, might be a good time to maybe zoom out and try to define what it is, what it isn't, how we try to define it. I would argue for engineering against natural hazards, it's just the level of acceptable performance. So I realize that the word is performance objective, and then I use the word performance in the definition. So I'll try and give you guys maybe an alternative one, but it's just like what we tolerate in our structures and our systems. There are potentially an infinite number of ways to define acceptable performance, both in terms of, different components in our system and their exposure to different hazards, as well as, how they should perform. They are generally developed, decided on, prescribed through seismic provisions and building codes. And the reason I'm harping a lot on building codes and provisions is because we talk a lot about, community resilience to natural hazards. And the minimum requirements, I tend to argue, is how you get that. A lot of structures are designed according to minimum requirements. Residential housing, not tall buildings are great, really elaborate structures are great, but the most of our risk exposure comes from stuff that's designed to minimum requirements. And so that's why, as unsexy as it is, we should worry a lot more about minimum requirements than we currently do. Alternative definition is that it really just tells us how earthquake resistant our system needs to be. If you're a structural engineer, and I'm not, it's going to define the selection of your structural system, how large the structural elements need to be. Again, not a structural engineer. If we don't have the luxury of engineered systems, it's going to guide when we have to worry about mitigating against actual geohazards or mitigating against the risk that comes from those geohazards, and to what degree we need to reduce either the hazard or the risk. So how do we define acceptable performance? We generally, if you're looking at a building code or a design provision or anything like that, they're what I would call engineering performance objectives. And that looks like something like a low probability of structural collapse over the lifetime of the asset. This is straight out of the ASCE 722 seismic provisions for new buildings. And that essentially, if we really dive down into the details of it, that's ensuring that our base shear and element forces might withstand our, just making sure that everything is behaving the way it's supposed to, that nothing fails and causes collapse. Again, if we go into geotechnics, those performance objectives become a little fuzzier, a little harder to define, but basically we don't want liquefaction to happen in an earthquake. We definitely don't want it to affect our structure. So this is kind of limiting our, for instance, settlement or tilt under some design earthquake loading is typically what we see in our seismic provisions. And I'll dive a little more into what design earthquake loading or how it's defined in a slide or two. But if you ask like a stakeholder, not an engineer, an owner, emergency managers, policymakers, I don't think they particularly are going to ask you to ensure that their base shears are limited or that their drifts are low enough. They care about societal performance objectives, which is, again, this is kind of a term I don't know how often it gets thrown around, but there's a clear difference between engineering and societal performance objectives. And actually, if we think about things in terms of societal performance objectives, it's a lot easier to articulate what we care about and what we value. So obviously, we don't want an earthquake to cost us a ton of money. We definitely want to make sure that things are repairable. We don't have to replace structures, and we want downtime to be minimized. Sorry, water. We care also about, increasingly about this idea of functional recovery. We want people to be able to resume their normal lives with minimal disruption. And that's, again, something that multiple folks, in this group, in this civil engineering department are looking at. It's this idea that life safety is not really exactly or everything that we need. Functional recovery is also really important. And then obviously we want to limit human losses, casualties, deaths. And, these are obviously related to each other. Engineering, societal performance objectives. And in theory, in a perfect world, if we had all the information available to us, we'd want to dictate what is our acceptable level of loss from a societal standpoint. How many deaths, how much downtime are we willing to tolerate? And then back out what engineering performance objectives we need to achieve that level of acceptable societal performance. In reality, we tend to set engineering performance objectives and then kind of hope that they achieve the societal performance objectives that we care about. So 1% probability of collapse, pretty reasonable life safety performance objective, but up until very recently, we didn't really consider what that does for functional recovery. In terms of liquefaction potential, it's even less, it's harder to make this connection. And so I guess what I'm trying to get at here is that, for every engineering performance objective we set, we have an implied societal performance objective, whether we like it or not, unfortunately. And we don't always have the tools at our disposal to know what that societal level of performance is. So if we are trying to limit liquefaction potential in a design earthquake, what are our expected annualized losses from that design earthquake? Are they actually acceptable to people? The other big thing is how consistent are they across different regions, different types of structures, different site conditions? Again, this is one of those things that really, it's an important component of seismic provisions, is ensuring that we have consistent, informed performance objectives, and we don't always have a guarantee that that's the case. Okay, so if we care about losses and we want to tailor our liquefaction hazards approaches to targeting some acceptable level of losses, we kind of have to adopt a performance-based approach, something that many of you might be familiar with. So that requires us to kind of go all the way back to the beginning of seismic risk and start to rigorously quantify our earthquake sources, the ground shaking that results from all of these rupture scenarios on all these sources, obviously liquefaction occurrence and effects, system damage, and then finally losses. And being able to take all the uncertainties inherent to each of those components, meld those together, come up with a probabilistic assessment of losses due to liquefaction in this case, or due to any natural hazard. I don't think we're close to getting there on the liquefaction side of things. We're very much rooted in the middle point of this. This is, again, where a lot of our time and effort in the last several decades has been focused. There's obviously a lot of great work happening to move us forward on system damage and losses. But again, my focus today is going to be on how do we take what we're currently getting in terms of liquefaction occurrence in the way people are analyzing these hazards, designing their structures against them, and setting ourselves up to be able to move towards something that looks like a demand or loss-based performance objective, those societal performance objectives. Okay, so to do that, let's talk really quickly about potential ways that we can define performance or risk objectives. We'll start very simple. Low liquefaction damage potential in an earthquake, in a strong earthquake scenario. Okay, so let's make sure that we're not incurring damage from a magnitude 9 Cascadia subduction event or a magnitude 7.5 San Andreas. Just like think of the big earthquakes that people talk about in society. We can take it a step further. We can kind of say, well, let's make sure we're not incurring damage under some target level of ground shaking, some probabilistically defined level of ground shaking, as we call uniform hazard based. This is something like the 2% in 50-year or 2475-year return period we see in the ASC 7 provisions, different return periods for AC 41, that's retrofit. But again, these are probabilistically defined ground shaking levels or design ground motions. We could take it a step further if we wanted to and just make things fully probabilistic. Let's worry about all ground shaking scenarios, and let's define a low probability of liquefaction damage over the lifetime of our asset. And this is where we start to get into things like uniform risk or uniform demand design basis. So this could look like a lot of different things. 2% likelihood of liquefaction triggering, some percent likelihood of manifestation, some percent likelihood of pipeline rupture, excessive settlement. You can, as soon as you start to get into these probabilities, you can start to devise some really refined performance objectives. Okay, so revisiting our scenario, deterministic hazard design basis. We define a worst case scenario. This is, I should always say, this is a scenario shake map for magnitude 9 Cascadia. It's not real. Everyone calm down. And we take a ground motion estimate from this magnitude 9.3 scenario, plug it into our cyclic stress ratio calculation, and we get our factor of safety conditional on our design, worst case scenario. This is a really intuitive way to look at seismic hazard and risk. You talk to emergency managers, policymakers, people that have to communicate these concepts to the public. Scenarios are a great way to do that. Like I said, easy to communicate, pretty easy to calculate. You might have 1 or 2, 3, a range of factor of safety calculations, but nothing too intense. You can still do it on a spreadsheet if you want to. Problem starts, and this is maybe something that you all have been exposed to when you are learning probabilistic seismic hazard analysis. A lot of the same concepts here, obviously. What's our worst case scenario? We can look at Cascadia, but Cascadia has a range of magnitudes and potentially magnitude 8s that occur more frequently than a 9.3. If you're in the Seattle area, the Seattle fault is a lot closer and a lot more shallow. We also have the South Whidbey Island. Which of these are actually going to be our worst case scenario? Which of these, we have a lot of different sources, a lot of different potential scenarios, different rates of occurrence. Deterministic design basis doesn't really account for that. Okay, let's take it a step further. Let's look at some of those limitations and then start to work through a PSHA-based design basis. This is our uniform ground motion hazard design basis. And this is where we take all of those uncertainties, rupture scenarios, magnitude frequency distributions, uncertainties in the ground motion criteria, or the predicted ground motions. And you can plug it into a PSHA calculation and you get this PGA hazard curve. This is the annualized rate of exceedance of various levels of PGA, and this black curve is sort of the aggregation of our individual hazard curves from all of our sites. And I've highlighted the 2475-year return period. Depending on our design basis, that's where we pull our PGA from. We also pull a magnitude. We'll talk about that later on. And that's our uniform hazard design basis. This is really common. This underpins most geotechnical provisions in a lot of codes. And it does account for all those uncertainties that we already talked about. It's a little more complicated, but about as tractable as it's ever going to be at this point. It's really easy there's tools everywhere to do it. The USGS has a bunch. Anyone can do a PSHA. The problem is we're considering just a single PGA, and we're also considering just a single magnitude. And I kind of just said that lots of magnitudes, lots of ground shaking scenarios might contribute to our hazards. So It's a little bit incomplete. We're also not considering uncertainties explicitly in liquefaction hazard assessment. This is a complicated problem, lots of uncertainties in your site characterization and actual liquefaction hazard estimation, and we're not really baking this in to this design basis. And then, the result of that being we can't really guarantee a non-uniform lifetime risk or probability of unacceptable performance. Okay, so let's take it a step further. That third bullet point I showed on the initial slide, which is that probability of liquefaction, that risk or demand targeted design basis. This is where we're taking our PSHA, we're taking the hazard curve, that PGA hazard curve, and now we're on log, or we're in linear space on the x-axis, and we're sort of taking some representation of our liquefaction fragility. This is, again, a very simplified, not real scenario, but I think it's a useful graphic, hopefully, to sort of walk through the risk analysis. So we're kind of combining these two components, ground motion hazard, liquefaction risk, and it enables us to kind of identify regions of the hazard space where maybe we have PGA levels that are exceeded relatively frequently, but they're going to be far too low to actually contribute to our liquefaction hazard. Conversely, we can identify regions where our PGA hazard is very high. It's definitely going to cause liquefaction should those levels be exceeded, but on an annualized basis, they're happening way too rarely to affect the liquefaction hazard or demands over the lifetime of our asset. And sort of doing this quantitatively allows us to weight these combined factors and kind of identify the areas in our hazard and fragility space where we think the liquefaction hazard or the demands are going to be concentrated. And again, this is sort of just an infographic. Hopefully it makes some sense. I'll kind of show you how it actually gets calculated in a second. So this forms the basis not just of probabilistic liquefaction design basis, but this is how we do structural collapse, potentially how we do functional recovery. Lots of different performance objectives are based on this concept. We can explicitly define our acceptable risk or our demands. If we can't get all the way to losses, demand's a good place to go. It's consistent, it's explicitly defined, it's informed, and it influences, or it reflects the influence of both sides of that equation, both our seismic hazard and our demand. The challenges are that it's a little bit harder to implement. You do have to have pretty thorough characterization of those fragilities, and there's a lot of different fragilities out there. It's also pretty hard to implement in practice. I would argue it's getting easier. And it's getting easier to the point where we do have some real life examples of this. People were talking about it as early as 1978. I don't think any of us were around in 78, hopefully, or not, hopefully, doesn't matter. But this was talked about in ATC 306, back when ATC reports had 3 numbers total. But this was talked about in 1978. It wasn't implemented back then, but it was clearly something that was being appreciated in this report and other early provisions. It was adopted for nuclear facilities in 2005. For new buildings, this is that collapse risk criteria in the ASC 710 supplement and has been in place ever since. Snow loads in ASC 722, so not even talking about earthquakes at this point. Bridges in the AASHTO guide spec that just came out, also being considered for functional recovery in the upcoming 2026 NEHRT provisions. So there's examples of this all over the place. And in every single case that I can think of, to meet the minimum requirements, the engineer doesn't have to do that full risk-based assessment because, again, it's quite onerous, it's quite difficult. But in each of these cases, equivalent design ground motions were developed that could approximate those risk-targeted design levels, with maybe the exception of 4305, the nuclear facilities. I might be wrong about that, but in every case, these were developed with the idea in mind that we don't want to, cause people to do a ton of work, too much work that's not available to them, resources that are not available to have to meet the minimum requirements. So there's obvious benefits here. Hopefully you're starting to appreciate those benefits, but I'll just summarize them. We have life safety objectives, and we want to be consistent with those across different hazards. So we have a collapse risk fragility, we have collapse risk performance objectives. We probably should have that across different types of hazards. We are accounting for all return periods, the full hazard curve space. And like I said, uncertainties in our demand prediction and truly uniform performance levels. And maybe further down the line, these types of performance objectives let us get towards societal performance objectives, which I referred to earlier, things that are based on what public policy dictates, cost-benefit analysis, bringing in a lot of factors that we can't really account for if we're just approaching things from the engineering performance side. Okay, back to liquefaction hazard. Broadly, liquefaction hazard is based on a uniform hazard design basis. So we have our factor of safety, again, unfortunately. We compute a CSR. It's based on a uniform hazard PGA, 2475 year or deterministically capped. The magnitude scaling factor, typically defined as a consistent earthquake magnitude, which is, I think, pretty vague from the provisions language. And I've included 3 cases here: Seattle, San Francisco, Charleston, very real hazard curves, very different regions, almost identical 2475 year PGAs. So what's going into the CSR is almost identical, but the hazard curve shapes at very different levels of shaking are very different. And so you can't really guarantee that the true liquefaction hazard is going to be the same because we're not accounting for those different hazard curve shapes. So that was on sort of the ground shaking side of things. We also don't really have a systematic way of accounting for, like I said, uncertainty in the prediction of liquefaction triggering. So we have this solid black line denoting liquefaction, no liquefaction. Really, that's more of a cloud or a shaded region. That's probably a lot wider than that. Liquefaction is a probabilistic limit state. We don't think about it in terms of yes or no. We really should be thinking about it more in terms of likelihood. And so that uncertainty comes from within model variability. If you notice, there's filled in dots on the higher side of the line and or the lower side. You have to make some decisions. There's some uncertainty here. We also have epistemic uncertainties from different types of models, different modelers, data sets, decisions being made, ways to interpret data, philosophical differences. This is good. It's good to have these uncertainties. And where we can, we should be able to incorporate them into our design guidelines. Currently, we don't do that. So one of the ways, probably the first attempt to assess and address those limitations is this idea of probabilistic liquefaction hazard analysis. This was proposed 15 years ago, or close to 15 years ago, by my old PhD advisor, Steve Kramer, with his student Roy Mayfield at the time. That won them the ASCE Norman Medal. Part of it, I think, is because return period of soil liquefaction is just a snappy title. The shorter your title can be, the more to the point it is. I feel like you're gonna have a good chance at that Norman Medal that we're all trying to get, apparently. But to my knowledge, and I could be wrong, this is probably the first time someone took this performance-based approach to engineering seismic design and analysis and applied it to geotechnics, specifically earthquake geotechnics, specifically to soil liquefaction. And it considered all the ground shaking scenarios, extending the USGS National Seismic Hazard Model, all those uncertainties in liquefaction resistance, and came up with what you see on the left here, which is this hazard curve of factor of safety. And that's, for the first time, we were able to assess on an annualized basis the probability of liquefaction. So what return period of liquefaction, what probability in some lifespan, 50 years, 100 years, is the liquefaction going to occur? So this is kind of how it looks in equation form. We're looking at a mean annual rate of, in this case, non-exceedance of factor of safety, because dropping below a factor of safety of 1 is actually what we care about. We do this through this conditional likelihood probability, conditional on PGA and magnitude, and this incorporates, again, those uncertainties that we talked about before in liquefaction triggering estimation. We also need to be able to account for the conditional magnitude likelihood, and this is, again, we can revisit magnitude disaggregation, start to get that full joint probability distribution, rather than just picking a single magnitude like engineers have to generally currently do. We go from conditional probabilities to annualized rates. We bring in the PGA hazard curve that we talked about earlier. And looking at that, this is numerically evaluated here, that incremental exceedance rate. And we do that over all magnitudes, all PGAs, to get that non-exceedance. And because factor of safety is an intermediate parameter in a lot of applications, we can look at a full range of factors of safety, not just factor of safety of one, and come up with this FSL hazard curve. Looks a lot like a ground motion hazard curve, it's just inverted a little bit. This is for a single site in Seattle, fake soil element, just looking at things very hypothetically. And with this, we can take the annualized rate at which our factor of safety drops below 1, the inverse of which, or the reciprocal, is our return period of liquefaction for Seattle. That's about 400 years, and we can assume a plus on process for better or for worse. And that corresponds to a liquefaction probability of 12% in 50 years. Okay, let's bring in Charleston and San Francisco. Those are the two hazard curves that we also looked at that all overlapped at the design basis PGA level. And these are the corresponding full PLHA hazard curves. And the results look pretty different. We can repeat this for San Francisco and Charleston. San Francisco, that probability in 50 years is about nearly twice as high as Seattle. Charleston, it's less than half of what we see in Seattle, really a 5-fold difference in probability across 3 sites that under ASCE design provisions would have almost identical liquefaction hazard. So we're starting to see the differences between the uniform ground motion hazard design basis and what would happen if we started to adopt a PLHA-based design basis. So we can start to invert this a little bit. We can look at the factor of safety at a given return period. Maybe that's our design basis. Maybe we decide that your 1 in 2475 year factor of safety needs to be greater than 1 for your probability of liquefaction to be acceptably low. So what would that look like? For Seattle, that just for this soil element, roughly 2% in 50 year would be 0.43 factor of safety. We can compare that to what we get from our ASCE 7 design basis. We're talking a lot about uniform hazard, ground motion hazard. The PGA for Seattle is actually deterministically capped. We can talk about that if you guys have questions about deterministic capping. So that PGA is quite a bit lower. And we can actually look at where that more simplified PGA sits on a probabilistic hazard curve for factor of safety and get what we refer to as an effective liquefaction return period. And for Seattle, that's about 5% 50 years or a 1,000 year return period. Let's repeat for San Francisco, also deterministically capped PGA. It's wild. And the differences are actually a bit more significant. Our return period is as low as 500 years, about 10% probability. And again, I'll get to that in a second, actually. Charleston are actually pretty consistent. Charleston also deterministically capped, but our factors of safety are very similar between the two methods, and therefore we're getting an effective return period of 2% in 50 years. So what does this really, I guess, what does this mean? Well, one thing, it means that a 2475 year PGA being plugged into a deterministic assessment of factor of safety is not going to give you a 2475 year factor of safety. And hopefully I managed to demonstrate that deterministic capping, which brings those PGA levels down, actually makes this even more inconsistent. So our actual design factor of safety return periods vary from, in this case, about 500 to nearly 2,500 years. And so what we're telling people, also liquefaction probability is 2 to 10%. So what you're telling an engineer in Charleston is your factor of safety greater than 1, that needs to correspond to roughly a 2% in 50 year acceptable liquefaction probability. So if your liquefaction probability is higher than 2% in 50 years, you need to start looking at consequences and sharpening your pencils. In Seattle, that acceptable probability is almost over twice as high. So much less stringent. And in San Francisco, it's nearly 5 times as high as it is in Charleston. And so what we're getting at here is a really inconsistent design basis, inconsistent levels of acceptable liquefaction hazard. But the other cool thing we're starting to do here is tease out something that resembles an implied performance objective. It's very rudimentary. still factor of safety based, but it's probabilistic. And this is kind of the power of using probabilistic methods, is that we can use them in these forward applications, but we can also use them to inform what our current design levels are when we don't use probabilistic methods. And so just to give you a broader sense, just to repeat, we kind of repeated these analyses as part of my PhD work for a bunch of sites and a bunch of site conditions, and more or less kind of confirmed those results on the previous slide. So what you're seeing here is a map of the implied acceptable liquefaction return period across the US. The areas in blue are going to be much longer return periods, and so more stringent design levels relative to the areas in red. So what we see in Charleston and areas surrounding the Charleston seismic zone is we are around 2% and 50. They're actually kind of, consistent with each other. We can take a little bit up higher in New Madrid, around 3% and 50. Pacific Northwest coast, areas that are dominated more by Cascadia than, for crustal seismicity inland, these are around 2%. So a lot of the country is actually consistent, which is remarkable. Where we start to run into issues is the Western US, particularly the areas dominated by shallow crustal hazards. These are using non-deterministically capped motions. Actually, this was just getting a sense of, we're using a uniform hazard design basis. What happens? It's actually worse if we have deterministically capped motions, but again, around 4 or 5%, 6%, 10%, and I think in San Jose was maybe the worst offender. So this is sort of our starting point. We can sort of get a sense of what our design environment looks like, and we can start to think about ways to move from uniform PGA hazard design basis to a uniform factor of safety design criteria. So something where a uniform return period factor of safety below 1.0 requires further investigation. Maybe it's a 2% 50-year, 3% 50-year. Maybe it's a little bit higher in those crustal areas. This is sort of bringing in the idea of cost-benefit analysis. And again, so this is kind of part of the strategies for establishing these criteria. We can consider what our current design return periods are, start to bring in the idea of population density in certain areas, hazard exposure, start to weight these results toward the higher hazard, higher risk areas, with the idea being that these are not risk-based criteria. Let's not pretend for a second we've solved liquefaction in terms of risk and societal objectives, but it's definitely a step in the right direction. With the long-term idea being that we can start to go from this midpoint here all the way over to demands, damages, and losses, and start to bring in cost-benefit based performance objectives. What is our current risk? That requires probabilistic analysis. How do different types of mitigation reduce that risk? What do those costs of the mitigation compare to not doing anything in terms of annualized costs? We can start to factor in broader economic implications too, things that don't typically factor in to these types of engineering analyses. What does mitigation do to affordability? We're in Boulder right now. There's an affordability crisis. Like it's not, these are conversations that need to be had. Environmental considerations. How much material is this going to cost to pursue mitigation versus what's the environmental impact of damage and destruction of infrastructure? Okay, just to put a bow on things, I think I'm maybe a little over time, but okay, cool. I don't know, hot take, liquefaction's complicated. You will see this throughout your careers if you continue to focus on liquefaction, whether it's in research or it's in engineering practice. There's a lot of uncertainties in every aspect of the problem, some that we can constrain right now, some that we need to do a little more work on as a profession. The problem being that we don't incentivize engineers to sharpen their pencils to meet minimum provisions. So what I'll say is, at the top of the field, the best consultants, the best practicing engineers, generally speaking, I think get it right. They do a really good job using engineering judgment, factoring in uncertainty where they can, with generally limited project budgets. So what you'll find, if you haven't done so already, is there's not a lot of budget allocated to the geotechnical side of things. And so with very limited runway, most engineers at the top of their field do a fantastic job of generally getting the liquefaction problem as right as they can. But at the bottom of the field, at the kind of the base level, the engineers that are trying to meet minimum requirements, that uncertainty isn't baked in. And so that's generally a problem, I think. We would like to be able to show the value of good geotechnical work, and we can't show that value if the cost of doing so doesn't reduce the overall costs on the project. So basically, I think what I'm saying is our minimum requirements should be way more stringent. But the result of all this is that we have these liquefaction, quote, performance levels that are kind of all over the place, very difficult to articulate. It took me 50 minutes to try to articulate a very relatively straightforward performance objective, and they're super variable. Is also what I've hoped to show you guys today. And also, they're not really performance levels; they're just not liquefaction levels. So that's also an area where we might need to make some progress, and we can if we start to use some of the tools at our disposal to start to make our way towards demand and risk targeted approaches. This allows us to evaluate our liquefaction hazards, our demands, our damages, our losses in an annualized sense, be consistent with current life safety and functional recovery objectives, and then hopefully in the future really start to make progress towards performance-based design criteria. Okay, thanks so much for having me. Thanks for your time and attention. And I don't know if you guys have time. I know there's a class next, but happy to answer any questions.
We have about 10 minutes till the class is scheduled. Let's move on there later. So I know Sheeta put a question in chat. I can start with
I'm
that.
nervous
People
now.
in the room have any questions?
Clap, right?
Yeah.
Yeah.